Okay, so we're going to talk about molecular formulas, and this is on page 8. So molecular formulas are different than empirical. Well, sometimes they can be the same because a molecular is the true formula. Empirical was the simplest ratio. So they are related. A molecular formula is going to be some multiple of the empirical. That's the important thing. It's a multiple. So you have to keep the ratio, which means you have to look at the subscripts. If it's a 1-to-2 ratio, you have to keep it in that same ratio. So what we have to do is sometimes a little bit of math, not hard math, a little bit of math to find out what is the multiple. It's always going to be a whole number. We don't have to worry about in those halves, quarters, thirds. We need to figure out what is the multiple of the empirical formula. So first, to kind of look at the conceptual and some multiple choice type, look at the subscripts. So if I see C2H4, you look and go, okay, can this be simplified? Yes, I could reduce this to CH2. So C2H4 is a molecular formula that has an empirical formula of CH2. That's how they're related. It was like, how did I go to that? Well, I took this and I just times everything times 2. That's how I got the C2H4. You can have multiple molecular formulas with the same empirical, because if I took CH2, you could multiply it by 4, C4H8. That would be another possible molecular formula. This is why we use prefixes for covalence, because they go together in different ways. So C3H9, first thing, is that an empirical or a molecular? So hopefully you look and go, okay, that is a molecular because you can simplify the subscripts. So its empirical formula would be CH3. Divide both by 3. But look at C2H5. I cannot simplify that one because we can't have any halves. So that is an empirical formula. Now, it possibly could also be the molecular, because if you look at water, H2O, that is its true formula. So molecular is the true formula, but it also has the empirical formula is the same. So sometimes they can be the same thing. So if you look, the question, what if I have an empirical formula, what is the empirical formula? You're just simplifying the subscripts. So you would divide them all by 2. And if you divide it by 2, you're going to get C2H80. So the empirical formula is the simplest, molecular is the true. I would definitely know those definitions. Okay, so how do I calculate it then? Well, you're going to use molar masses. Kind of circle that, highlight it. That's what we're going to use is molar masses. So take the molar mass of the true formula, divided by the molar mass of the empirical. You're just trying to see how many times greater is the molar mass. Because the molar mass, if it's 2 times greater, well, that's because you have twice the amount of atoms. If the molar mass is 3 times greater, you have 3 times the amount of atoms. So it's just based on how many atoms you have in that formula. That's what the molar mass is going to be. So we have this one, okay? Look at the wording, determine the molecular. If you have the empirical, and it gives me the molar mass. So the molar mass of the true formula is what is going to go on top always, but we need to figure out the empirical. Now, this is the one time I'm going to say we can round because we know we're going to get whole numbers. I take it just to the 10th. So don't worry about writing all the numbers when we're doing this calculation. So I go 3 times 12 plus 2, and I take that 15.999 and round it up. So that's where I take the molar mass of this guy, C3, H2, O, find the periodic table, add it up, and I am rounding, yes, because I'm not doing mole calculations. It has a molar mass of 54. So I'm saying, okay, so 216 divided by 54, how many times greater is that? Well, that compound has 4 times the mass. The only way that a compound could have 4 times the mass means you have 4 times the atoms. So take the empirical, so take these numbers, or just multiplying it by 4. So C12, H8O4. You've just calculated the molecular from the empirical. So look at the next one. So I have an empirical of B2H5. I know the true formula has a mass of 54. So what is the formula? So again, I'm going to take it to the tenths because boron isn't a whole number, but take the mass, find your periodic table, 2 borons plus 5 hydrogens. It has a molar mass of around 26.6 grams per mole. That came from boron. So 54 divided by 26.6, yeah, that can round up to 27. 2, if you do not get a whole number, now close enough to a tenth of a whole number, like I said, there won't be any halves, quarters, thirds. If you get a weird number here, you found the wrong molar mass, go back and fix it. And so 2 means 2 times everything. So 2 times 2 is 4. 2 times 5 is 10. That's how I found my empirical formula, molecular formula from my empirical, excuse me. Okay, so now if you're looking, you have 2 of them, B and C. Go ahead and do B and C, and then we will check your answers next class. So I want you to go ahead and answer B and C just how we did the first 2. Okay. Now, if you look the next one, it's really just a combination because I didn't give you the empirical formula. So since I didn't give you the empirical formula, first you're going to have to calculate the empirical formula, then we can do that step. So when you're reading this, just realize there's a number you don't need right away. So this 180, we're going to kind of tuck it away. Don't do anything with that yet. So this is doing like pages 7 and what we did the whole day doing the empirical formulas, empirical airlines. We just need to calculate the empirical formula. So list what we have. We have carbon, hydrogen, and oxygen. So I know that there's 31 grams of carbon. I have 5.2 grams of hydrogen, and I have 42 grams of oxygen. So remember with empirical, we like grams in the lab, but we can't do calculations with grams. So we know we're going to have to change all my grams to moles. Again, this is what we did all last class, or all this class, depending when you're watching this. Molar mass, that I know a lot of you probably know these masses, 12.011 gram. Molar mass of hydrogen, 1.008 grams. Sorry, stylus isn't working. 1 mole of oxygen, 15.999 grams. So we're going to get the answers. 2.5, don't round. That's how many moles of carbon. How many moles of hydrogen? How many moles of oxygen? Okay. So we can't leave it there. So then our next step, remember we divided them by the smallest. So the smallest in this one, there's my smallest. So I'll divide them by 2.583 because we need to get to a whole number. That's a 3. So this turned to 1. This was 2. This was 1. So my empirical formula for this compound is CH2O. Okay. Yay, I'm done. No, wait. Oh, no. No, I'm not. Because look what it asked. It asked for molecular, not empirical. So now we have to do what we were just doing above. Now I need that 180 grams. So now I know I have a molar mass of 180 grams. So get the molar mass of this guy. Get the molar mass of what you just calculated, your empirical. So 1 carbon plus 2 hydrogens plus an oxygen. So if you add that up, it has a molar mass of 30 grams per mole. That's that molar mass. So 180 divided by 30, it's 6 times. Yikes, sorry about that. Okay, so where we ended up, you can go back if you need it. We know it was 180 grams divided by the 30 grams per mole. Yes, these are both per mole. That's why they go cross out. So it was 6 times the mass. So we knew our empirical was CH2O. So 6 times the mass means you have 6 times the atoms. So take all your subscripts and multiply them by 6. Glucose. Okay. Number 7, I've left for you. We'll kind of do that together in class. I would go ahead and get started. Then if you have any questions on it, we can talk about it. So the rest of class, we're going to be finishing the worksheet and then doing some review because test will be happening the following class. So come with questions and we will see you next class.